Okay, the next problem says you wish to graph the following relationship, the number of diamonds owned by 20 people, one of whom is a multi-billionaire. Now, logarithmic scales, they help us to basically squash down the data when it's too high, when certain values are off, too high. So you're going to find these a lot in your college classes. You'll see these a lot in history and science, where you basically want to graph some data where you can actually see it. So instead of graphing so this is the first person, this is the second person, this is the third person, instead of graphing like 10, 20, 30, that wouldn't make any sense here because the first two people could have one diamond. And the multi-billionaire could have multiple diamonds, for example. So this scale might not be super helpful the way that it is right now. So instead, what you can do is you can make it logarithmic, where you make this like 10, this would be then 100, and this would be then 1,000. So you're multiplying, each increment you're multiplying by 10, 10,000, and so on. That's a logarithmic scale. And it can be helpful to basically take data that is exponential or that varies strongly and make it more linear and make it something that you can actually see on a graph with all the data points being represented. Okay, the next problem wants the domain of this function. Once again, if we change this in exponential form, 8 to the y equals 8 minus 4x, you can see that this must be positive because there's nothing I can raise 8 to get a negative or 0. So I'm going to take 8 minus 4x and set it greater than or equal to 0. Subtract 8 from both sides. Divide by negative 4. And you get x is less than or equal to 2. That's my domain. I'm going to write that as 2 and then negative infinity all the way up to 2, including 2. So negative I and f, comma, 2 bracket. The range of the function then, actually this should be parenthesis, I'm sorry. This can't be 0. It's got to be greater than 0. So this is going to be less than 2, right? Because you can't have 0. There's nothing you can raise 8 to get 0. So that should be parenthesis. Now the range is all real numbers, and it is for all these functions because they're reciprocals of, this function is a reciprocal of the exponential function, 8 to the x basically. So this function is going to go like this, where the range is going to be all real numbers. Actually, you can graph this if you want to look at it. It's been reflected as well, so it looks like this. And I know it's a graph for error. Everything does go down to negative infinity, and it does. You can't really tell, but it keeps going off slowly. But it does go up to positive infinity. So the range is all real numbers, but x's are all numbers less than 2. So find the domain algebraically, and the range of these log functions is always going to be all real numbers. Okay, the next problem then says the graph of this function can be obtained from the parent function by one of the following. Well, if we subtract 5 from x, we move the 5 to the right. So we'll be shifting it 5 just to the right. So we put a here. The domain of the function, keep in mind, if you change this into 4 to the y equals x minus 5, you know that there's nothing you can raise 4 to get a negative number here, so x minus 5 has to be greater than 0. Can't even be 0. So if you add 5, you get x is greater than 5. So that'd be 5 to infinity, not including 5. The range is all real numbers, as it is for all of these, negative infinity to infinity. And the x-intercepts occur where y is 0, so plug in 0 for y right here. Plug in 0 for y, you get 4 to the 0th is 1. So you're solving for x, so add 5, you get x equals 6. So the x-intercept is at 6. I think it wants it at 6, not an ordered pair, but if not, try the ordered pair, obviously, where you plug in 6 comma 0. And the vertical asymptote of the function. We can graph this and see. This gives us an idea anyway. The vertical asymptote is somewhere around here. We actually know where it's at here, and I'll explain. But this function goes like this. The range is all real numbers. This thing does keep going down. It's a graph for error. You have to type it in like this, by the way, using the change of base theorem. Just do the log of the top divided by log of the base. Do the change of base theorem, which is on our formula sheet right here. So you just take the log of x over the log of b. And you can use any base you want. You can use base 7, base 10. I usually use base 10, obviously, because you don't have to write it then. Like in decimals, for example, that is base 10. But we're going to have to look at this real quick. Now, the asymptote is, we know that when we look at this, 4 to the y, we know that there's nothing we can raise 4 to get 0 or to get a negative number. So at the end of our domain at 5, that's where our asymptote is. And you can see that from the graph as well. At x equals 5, y can be anything. That's the vertical line. That is the asymptote for this function. And so x equals 5. And basically, we know that normal logs look like this, where the asymptote is x equals 0. But if we shift this thing over 5 units to the right, then the asymptote becomes a line x equals 5. So there's different ways to look at it. But where our domain starts, there is the asymptote there, which in this case is 5. The next problem is similar, problem 9. If we add 8 to log, that shifts it up. So we want to shift this upward 8 units, so that'd be C. The domain of this function is x that is greater than a. Find the values of a. So we know that the regular log base 4 function looks like this. And if we shift it up 8 units, it just moves up like this. Doesn't actually change anything about the domain and range. So that'd be 0. The domain is all numbers greater than 0. The range of the function is still negative infinity to infinity, and you can tell that it is. This thing goes down forever, and it goes up forever. So I would say yes right there. Okay, the next problem gives us this log function and a point. If we plug that one point in, we get 1 equals log base a of 6. If we change it in exponential form, it would be a to the first equals 6. So what do we raise to the first power to get 6? Well, that'd be 6. So a is 6. Next problem, same thing. Plug in 1 for y, and plug in 38 for x. Change in exponential form, base to the exponent equals the argument. And you'll see that when you raise something to the first power to get 38, that'd be 38. Okay, the next problem tells us, it wants us to say, as x goes to 0 from the right, what happens to this function? Well, we can graph these. You can use decimals if you want, but we know that the regular log function looks like this, right? It's a reciprocal of the exponential function, or I'm sorry, it's the inverse of the exponential function. So it's a reflection of the line y equals x. But this thing is, we have to change the sign on the y value, which reflects it over the, if you change the sign on the y value, it reflects it over the x-axis. So this function would look like this. And so we can say as x goes to 0 from the right, this thing goes up to positive infinity. So we just say they want us to type it all out. I know they're getting picky with these, but make sure you type it all out. And then as x goes to, the next function is a different function. That's the natural log of negative x. The natural log looks like this, like any other log. But then if we change the sign on x, it reflects it over the y-axis, so it goes like that. So as x goes to 0 from the left, this goes to negative infinity. So we type in negative infinity. All right, I hope this helps.